Last time, I talked about the various ways of representing numbers physically, and I showed how digits could be coded either mechanically or electrically. And to do arithmetic with a machine means that you have to manipulate these representations so as to produce new numbers from old ones. The big revolution in computing came when we started using electronic methods for the arithmetic. This opened the way for all the steps in a calculation to be done purely electrically, with no mechanical motion involved, and at enormous speed. So a very long calculation could be done in a few seconds. Now, in the course of doing a very long calculation, you produce a lot of numbers. Some of these you want to keep. They're part of the answer, but most of them are only intermediate results. You remember we did a little example last week of a short calculation in which we had to store some quantities as we went along. And you're going to use them later, perhaps several times, but you don't want them once the calculation is finished. They're only of temporary interest during the calculation. All you really want is the number at the bottom, which is the answer. All the rest are simply temporary intermediate results. And in a long calculation, there may be hundreds or thousands of them. So one of the requirements in an electronic computer is a way of remembering these numbers or storing them. We must have a device that can accept and remember a lot of numbers at great speed, as fast as they can be produced by an electronic arithmetical unit, and can give any of them back when needed, also at very great speed. In earlier machines, this problem of storage didn't crop up very much, because they were so slow that they were only given short calculations to do. The numbers involved could all be kept in the same piece of machinery that did the arithmetic. But to make use of electronic speeds, we needed storage for many more numbers. So it was decided to separate the storage part from the part that did the arithmetic. And the designers started looking for ways of storing many numbers cheaply and recalling them again, all at very high speed, without changing any of them. All the other parts of a computer could be made using techniques like those developed for radar. But storage was a new technical problem, which marks the beginning of computer engineering. One early storage device was the so-called delay line. The idea was to put a rapid succession of electrical pulses into something that would delay them for a considerable time. So long, in fact, that you could put several pulses in at the beginning before the first one came out at the other end. Then, as they emerged, they could be amplified and fed back again to the beginning, so that the same set of pulses would keep on repeating themselves over and over again. Now, if you want to read out the numbers at any time, all you have to do is to take the signal from that point and send the pulses to wherever you may need them. And if you want to store fresh information in the delay line, you could just temporarily break that recirculating connection and feed some fresh pulses in from another source. And when you got the new pulses in the delay line, then you could make the circulation again, and so the numbers would then go on repeating themselves indefinitely as fast as you wanted them, as long as you wanted them. Now, electrical signals go very fast indeed, and although it is possible to slow them down somewhat, it isn't easy to make a good delay line for storage this way. But sound waves are nice and slow, only about 700 miles an hour in air. So the electrical pulses can be converted into sound waves, pass slowly along the delay line as sound waves, and then converted back into electrical pulses again to be amplified and go into the beginning. So they continue going several times around, slowly through the delay line, and quickly back in electrical form to the beginning again, like this. Here is one of the early forms of delay line that was used. In this tube here, we have a certain amount of liquid mercury, which is the medium through which the sound waves travel. This steel tube is just a container for the mercury, a tank, if you like. In fact, these early delay lines were known as tanks for the memory, if you like. The mercury occupied just the middle part of the tube here, and at each end of it there was a quartz crystal which converted the electrical signals into sound waves as they went into the mercury, and then back into electrical signals again to be amplified and put back into the beginning. And so that way we could store a pattern of pulses for any length of time which could represent information or numbers. And later we found ways of making the sound go not through liquid mercury, but through an actual solid piece of wire. Just inside this little unit here, you can see a short length of wire which carried the sound waves from here to here. The sound took about 30 millionths of a second to get from one end of the wire to the other, and it was possible to put about 15 pulses into the wire before the first one emerged from the other end. They were then amplified by components inside the box, which were connected through the circuitry that you can see on the back here. In fact, very much longer pieces of wire than this were also used, which could store many thousands of pulses at a time. And there were other types of store also used at the beginning, but nowadays these stores have all been replaced by what's called the magnetic core store. The basic element of this is the magnetic core, which is a little tiny ring of a magnetic material called a ferrite. I've got some here in the palm of my hand. They may look just like tiny specks to you, but in fact each one of these is a complete ring of magnetic material. And here we can see a magnified picture of just 4 of these little rings with the point of a needle to give you some idea of their size. Now, each one of these rings can carry lines of force either clockwise or anti-clockwise. It could be put in 2 possible states, in fact. It could be put in either of those states by passing an electrical pulse along a wire threaded through the middle of the core. Here is an assembly of these little magnetic cores as used in a computer. There's about 1,000 of them here in a rectangular array, threaded on a number of wires which carry the pulses that switch the cores into their 2 different states. And here is a magnified picture of a similar array, just like the ones used in modern computers. And here's a magnified picture of a similar array. At each of the intersections of the wires there, you can see a little lump, which is a little ring of this magnetic material. And it's possible, without going into details, it's possible to read off any part of that magnetic pattern again as a set of electrical pulses in the same form in which it was put in. Well, a big modern computer usually has at least 1 million of these cores threaded on a mesh of wires like that and arranged so that any number can be read or changed when required. You can put a new number into the store or reproduce it again in a couple of millionths of a second. I said numbers, but we've been talking about electrical pulses and magnetic patterns. How do we use these patterns to represent numbers? Well, the patterns are of a particular kind. Each magnetic core can be magnetized in one of 2 ways. Likewise, a delay line may at each moment emit a pulse, or it may not. Again, 2 possibilities. In fact, it's a lot easier to make a circuit that only has to discriminate between 2 different possibilities. Magnetized this way or that, passing an electrical pulse or not passing a pulse. And because of this, many computers use a number scale in which each digit has only 2 possible values instead of 10. This is the scale of 2, or the binary scale, in which each digit is either 0 or 1.